Hello class, good evening. We have a new topic. This is design of DRB or Doubly Reinforced Beam. So ito yung section. Dalawa na ang kanyang reinforcement. You have the tension steel or AS and then you have the compression steel which is A'(S). Compression in the sense na nandun siya sa taas ng neutral axis. Remember na anything na nasa taas ng neutral axis, that is compression. And then anything below the neutral axis is tension. Okay, dito sa tension steel, we have T which is ASFY. And then sa compression area sa taas, meron tayong compression block, yung shaded area, which is defined by this rectangular block na A tsaka yung 0.85 F'C. And if you will take this area, this is C sub C, which is compression concrete, which is equal to the area of the block, 0.85 F'C times A times your B. And then, again, still on the compression area, you have the A'S, which is defined by CS or compression steel. And then, the tension reinforcement is required to yield by the NSCP. Thus, the tension force is always T, which is equal to ASFY, or this is also TS. The concrete compression force is C sub C, which is equal to 0.85 F'C times AB minus A'S. Take note that the concrete area is actually a rectangle with holes, and the holes representing the area occupied by the compression bars A'S. So, dito, tinanggal natin ngayon yung area ng compression steel. This is for your C sub C. The steel compression force CS is equal to A'S times FSC, where FSC is the stress of the compression steel. This compression steel stress is based on Hooke's law. So Fs is equal to ES times strain in steel, which should be equal to or lesser than Fy. Take note na hindi pwedeng lumampas ng yield stress yung compression steel. From the strain diagram in figure 3.6, ito siya. Strain is equal to C minus D prime all over C times 0.003. Or, ito yung triangle na yan, ano? So, 0.003 over C compared to strain in CS over C minus D prime, okay? So, D prime, that is the centroid of your A'S from the extreme fiber. Ayun, C minus D prime. Therefore, your FSC is equal to C minus D prime all over C multiplied by 600. Yan yung 0.003 multiplied by elasticity of steel na 200,000. The concrete rectangular block with holes is difficult to handle. Therefore, the analysis is simplified by combining the two compression forces CC and CSC. CC, ito yung compression in the concrete. And then CSC, this is compression in the steel. Okay, so combining the two, compression concrete tsaka compression in steel, 0.85 F'C times the quantity AB minus A'S. Take note na minus yung area ng steel. Plus, yung A'S times FSC. Stress in the compression steel yan, ano? So, this is equal to 0.85 F'C AB plus A prime S times the quantity FSC minus 0.85 F prime C. Take note na si FSC, ito siya, okay? This is equal to this equation. So, kailangan natin ng regular polygon para merong kang distance, okay? Para ma-solve mo yung kanyang moment. The above two forces now have areas that are regular polygons. The locations of these forces resultants are easily determined. So, for C sub C, ang kanyang lever arm would be D minus A over 2. Okay? So, C sub C, that is at A over 2. Yung gitna niyan. Ano? Tapos, yung C sub S naman, ayan, C sub SC, ang kanyang lever arm would be D minus D prime. Ang location nung compression sa steel is nasa D prime. Okay? Ayan. So, ang kanyang nominal moment would be equal to CC times the lever arm D minus A over 2 plus CS times D minus D prime. Doubly reinforced rectangular beams are resorted to if the beam size is limited but the moment to be resisted is too high that a singly reinforced rectangular beam design is not enough. Now let's go back to SRB. So, i-multiply mo yung T times the lever arm na D minus A over 2. Meron kang moment. Pero kung minsan, yung moment load is mas malaki kaysa sa capacity moment nung tension steel alone. So, that's the time na i-consider mo rin yung compression steel na A prime S. Ordinarily, rectangular beams have top and bottom reinforcements and the corner bars are where the stirrups are tied to. However, the analysis and design approach is done using the concept of a singly reinforced section as a first recourse. The moment capacity using the concept of a singly reinforced section when the section is actually doubly reinforced will be a little bit smaller than the later. Note that these two instances, the tension force TS does not change and is still equal to ASFY. So, yan ang kagandahan ng singly reinforced beam. Yung AS mo, laging nag-yield. The only difference between singly and doubly is the lever arm between TS and the compression resultant of the forces CC plus CS will be slightly higher due to the presence of CS. Okay, CS, this is compression in steel. Hence, treating a doubly section as a singly section is actually a conservative simplification. To ensure that the beam section will be ductile, the NSCP requirement for a minimum tensile strain of 0.004 has to be complied with. So, ayan, sa steel, 0.004. From figure 3.7 below, where the strain of tension steel is set at 0.004, the following equations can be formulated. So, dito sa summation forces horizontal is equal to 0. Meron tayong tension steel, remember, AS. Tapos, meron tayong compressive force due to the concrete block, which is C sub C. And then, meron tayong CS or the compression force contributed by the A prime S. So, lahat ng nasa ibaba, which is TS, is equal to lahat ng nasa taas, which is C sub C tsaka CS. And then, remember that tension is equal to ASFY is equal to compression concrete 0.85 F prime CAB plus compression in steel, this is A prime S times FSC minus 0.85 F prime C. And then we have here two forces. Ito yung SRB. Take note, meron tayong rectangular block and then yung centroid niyang rectangular block na yan yung C sub C. Ito yung singly reinforced beam part. So, mapapansin mo dito, naging TS1 na siya, or that is AS1FY. And then, yung excess moment niya na M2. Okay? Ang ibig sabihin ng M2, ito yung moment above sa capacity ng SRB moment, or ito yung excess moment. Ito ngayon yung bubuhatin ng compression steel na A'(S), which is at D'. Ayan siya. So, ito magiging C sub S. Kaya siya naging M2, ang lever arm niya, D minus D'. So, dividing both sides of the equation with BD times F'Y. Okay. And substituting the expression A is equal to beta C, tapos yung ratio na C over D is equal to 3/7. And then your steel ratio, which is rho is equal to S all over BD. And then yung rho prime, which is equal to A prime S all over BD. Okay, dito dalawang ating steel ratio. You have rho, tsaka yung rho prime. Yung rho prime, this corresponds to your compression steel all over BD. Yung rho, this is your tension steel na AS all over BD. So the above equation is simplified below. Okay? So, ito ngayon yung magiging equation ng ating rho max is equal to rho max, which is equal to beta 1 times 0.85 F from C all over Fy times the quantity 3/7. In the above equation, FSC is assumed to be equal to Fy, which is a reasonable assumption for an over-reinforced beam. The equation is then simplified further. So, rho minus rho prime times the quantity 1 minus 0.85 F from C all over Fy. This is equal to your rho max. Now, let's go to the analysis of doubly reinforced beam. The analysis procedure for a DRB is outlined below. For this analysis problem, all relevant data needed to determine the moment capacity are given. This include the beam dimensions, B, ito yung width ng beam, D, the effective depth of your tension steel, D prime, that is the effective depth of your compression steel, tapos yung tension steel, which is AS, and then your compression steel na A prime S. And of course, you have the material properties, F prime C for concrete and Fy for steel. So, step 1, as in, parehas lang nito yung singly reinforced beam. Determine beta 1, this is based on your F prime C, tsaka yung rho max. Step 2, determine rho, which is equal to AS all over BD, and compare with rho max. If rho is less than rho max, then analyze the section as SRB and follow the procedures for singly reinforced beam. The compression bars are conservatively neglected in the analysis since the tension force T does not change and only the lever arm is slightly changed in determining the moment capacity. So, ito yung una nating checkin, yung rho, tsaka yung rho max. Notice na yung rho, yan yung AS all over BD. Okay? Tapos, you can pair this with rho max. However, if rho is greater than rho max, ibig sabihin, marami kang bakal. Okay? Parang over-reinforced siya. Then, analyze as doubly reinforced beam and follow the steps discussed below. Okay, so looking back here again, if rho is greater than rho max, ibig sabihin over-reinforced siya. kailangan tatapatan mo siya ngayon ng katumbas niya na concrete compression. Tatapatan mo siya ng katumbas na compression force, which is dyan papasok yung ating A'(S) or yung compression steel. Okay, so step 3, determine now your rho prime or your compression steel ratio. So this is equal to A'(S) all over BD. As in previous codes, it is assumed at this point that the compression bars yield and the equilibrium equation corresponding to a strain of 0.004 for tension bars become beta 1 times 0.85 prime C all over Fy times 3 all over 7. And then step 4, compare rho minus rho prime with rho max and determine the effective AS. Okay? Rho minus rho prime. So again, yung rho AS all over BD, rho prime A'(S) all over BD. If rho minus rho prime exceeds rho max, then consider only the amount of tension steel satisfying the code requirements. So, remember tension steel, or that is AS. Ito yung kanyang equation. Otherwise, the original AS is fully effective. In the succeeding steps, the stress in the compression bars has to be determined. However, the stress will depend on whether the bars will yield, in which case the stress will be equal to the yield stress, or the bar will not yield and the stress will be determined by the formula from Hooke's law. It is easier to assume that compression bars yield, which can easily be confirmed later. In this case, the equilibrium equation for summation forces equals 0 becomes, ito na siya. So, compression concrete is equal to TS minus CS. Take note na originally na tension is equal to compression, okay? So, yung tension, ito yung TS, tapos yung compression, meron tayong CC tsaka yung CS. CC, ito yung compression concrete. CS, ito yung compression steel. Okay? So, in-isolate natin dito si compression concrete, which is equal to tension minus compression in steel. So, or this is equal to 0.85 times F'C AB minus ASFY minus A'S times the quantity Fy minus 0.85 F'C. Okay, so solving for A and consequently C, we get step 5. Assume that the compression bars yields. So, yung equation ng A, galing yan dito. Inilabas lang natin si A. In-isolate natin siya dito sa left member. Okay? And then, eto makukuha na natin si A, given naman si AS, given din si A'S, given din si F'C, and you can easily solve for A, and then you divide that by beta 1, you get the small c, or the location of the neutral axis. And then step 6, solve for F'C. Ito yung stress nung compression steel using Hooke's law and confirm that this exceed Fy. So F'C is equal to C minus D prime all over C times 600. This should be greater than Fy. The above formula is taken from the strain diagram of the beam section shown below. Ito yung strain diagram. If the assumption that the compression rebars have yielded is confirmed, or this is F'C greater than Fy, then the moment capacity can now be derived. Okay, so pag nag-yield, or ibig sabihin greater than your Fy, yung compression steel, okay, pwede mo nang solvein yung moment. Take note, ang assumption dito, laging nauunang nag-yield yung tension steel, okay? And then, dapat mag-yield na rin itong si compression steel, and then you can take the moment. Step 7a, moment capacity if compression bar yields. this is VMN is equal to 0.90 times the quantity 0.85 F prime CAB times D minus A over 2. Okay. Ito yung value ng compression concrete. Tapos, ito yung lever arm. Okay, remember that? D minus A over 2. Next is yung moment due to the compression steel. Yan yung A prime S. And then, yung lever arm niya na D minus D prime. Okay? So, ayan ang kanyang nominal moment. That, ulitin ko, yung nominal moment is equal to 0.90 times C sub C, okay, times the lever arm na D minus A over 2 plus A prime S times Fy minus 0.85 F prime C. Ito naman yung compression steel, okay, times D minus D prime. And then step 7b, if the compression bars do not yield, as in step 6 is less than Fy, the expression for the equilibrium equation becomes more complicated. So, dito ka na ngayon gagamit ng quadratic equation. Okay, so 7b, hindi nag-yield, that is less than Fy. Okay, so, using the expression in equation 1 and 14 and substituting in the above equation leads to A as Fy is equal to this equation. Multiplying both sides of the equation with C yields to a quadratic equation. Okay? So, I will not be explaining so much on this quadratic equation. Pero, ma-appreciate natin to pag ipapasok mo yan sa Excel. The coefficients of the quadratic equation above are determined to solve for small c. So, ito yan. Ito yung quadratic equation. Meron tayong capital A, capital B, capital C. Tapos, ito na yung quadratic equation to solve for small c. Okay, this is equal to B plus the square root of the quantity B square plus 4AC all over 2A. Okay, so ito yung general equation ng quadratic. Wherein, yung letter B, capital B, is ito siya. A as Fy minus 600 A prime S plus 0.85 F prime C times A prime S. Take note na given yung mga yan. No? Tapos, yung capital A, this is 0.85 F prime C beta times B. Given din yan. And then, yung capital C, ano? Hindi to yung location ng neutral axis. Hindi rin ito compression force or anything whatsoever. This is simply equal to 600 times the compression steel area multiplied by the prime. Okay? Step 7, B-2. Note that only the positive root of the quadratic equation is relevant and the stress in the compression steel can now be evaluated. Okay, so ma-check mo to, dapat less than Fy yan. And then also, your new value for A is beta 1 times C. And the moment capacity is now given as this one. Ang moment capacity niya is simply parehas lang nung una, nagbago lang yung small c niya. So let's take an example. The beam shown above has a height of 600 mm. So ito yung overall height, ano? From the top to the bottom of the beam, overall height, and a width of 300 mm. Determine the maximum safe live load that the beam can carry. The dead load is the beam weight plus a superimposed load of 15 kN per meter. The stirrup size is 12 mm. The top bars are 220 mm. Ito yan, which is A prime S. And the bottom bars are 5 pieces na 28 mm. The clear distance between layers of bottom bars is the bar size 28 mm. Okay, so 5 28 mm yan, tatlo sa baba, tapos napatungan ng dalawang 28 mm din. And then, take note that ang clear distance dyan is 28 mm also. So, use 30 megapascal concrete and grade 60 rebars and concrete cover of 50 mm. Kapag grade 60, gagamit ka dyan ng 414. So, ito na yung kanyang solution. The capacity in an analysis problem can be determined independently since all the needed information is provided. So, we have A prime S, 628, AS, yan yung 5 piraso, 3,078.8 mm squared. And then, the effective depth D is measured from the top of the beam section to the centroid of the bottom bars. Okay, since 5 ito, and then magkapatong yung dalawang layers, ang centroid niyan ngayon is ito, okay? Which is defined by Y. Kaya ang effective depth D niya would be equal to D is equal to H minus this distance Y. So yung Y, ito yung centroid nung 5 rebars, okay? So, paano kung ang bakal naman natin magiging, let's say, 6 na 28 mm, okay? So, ang centroid nun is simply nasa gitna lang nung dalawa. Pero take note, ito 3 tapos 2. Kaya magkaiba ang kanyang distance, hindi siya exactly nasa sentro. Okay? So, the procedure can now be followed. Step 1. So, you solve for beta 1. And then, you solve for rho max. And then, you step 2. You solve for the actual steel ratio. This is AS all over B times D. And then, let's compare this with rho and rho max. Ayan o. Rho is 0.02 tapos yung rho max 0.022. So, it is less than. Therefore, the section will be analyzed as a singly reinforced rectangular beam and the procedure outlined in section 3-1.3 before will be followed by starting from step 5 in that procedure. Ito yon. If rho is less than rho max, then analyze the section as a SRB. Okay, so balikan natin siya. Ayan. Rho is 0.02 which is less than rho max 0.022. So, analyzed as a singly reinforced beam. So, ibig sabihin ng SRB, yung AS lang ang i-consider mo. Huwag mo nang papansinin pa si A prime S. So, ang nominal moment mo ngayon would be AS lang. AS Fy multiplied by D minus A over 2. I-disregard mo na si A prime S. So, yan ang capacity moment nung section. Next, using the beam in example 3.3, determine the moment capacity if the bottom bars are 5 pieces na 32. Yung using the same example, ito magiging 32 naman na. So, magiging 5 pieces na 32 mm ang kanyang AS. But still, yung kanyang A prime S is 20 mm na dalawa pa rin. Okay, so step 1, you check the rho max. The effective depth will change slightly. Okay, so ito naging 32. So naging 496.4. Bumaba siya ng konti. And then step 2, you compute your actual rho, which is AS all over BD. And then you compare this with rho max, no? So yung rho natin is 0.027. Tapos yung rho max, ito 0.022. Notice na exceed niya. And therefore, kapag rho is greater than rho max, ibig sabihin over-reinforced, kailangan mong tapatan ng compression steel. So, this will now be analyzed as DRB. Okay? DRB kapag rho is greater than rho max. And then, proceed to step 3. This time, consider na natin si rho prime, A prime S all over BD, which is rho prime equal to 0.0042. And then, step 4, compare rho minus rho prime times this quantity with rho max to determine the effective AS. So, your rho minus rho prime primes the quantity 1 minus 0.85 F prime cell over Fy is equal to 0.023. This is greater than the rho max na 0.022. Since the maximum still limit is exceeded, the effective tension still area is reduced accordingly. Okay? So, ito ngayon yung ating bagong AS, magiging 3874.92 mm squared. So, you simply follow this equation. And then, step 5, assume that the compression bars yields. So, your A would be 177.79. Ito yung kanyang equation. After solving for A, you divide that by beta 1 and then you have the location of your neutral axis small c. And then step 6, solve for FSC using Hooke's law. So FSC is equal to C minus D prime. D prime, ito yung location ng compression steel. And that is equal to 396.94, which is less than Fy. So, again, ko-compare natin to, ano? So, the above results indicate that the compression bars do not yield. Ibig sabihin, less than 414 siya. Thus, step 7B is followed. Ayan. So, pag dito sa step 7B, mag-quadratic equation ka na naman. Ibig sabihin, babaguhin mo yung value ng small c. Hanapin mo yung bagong value niyan, which is defined by your capital A, capital B, and then capital C. Notice na sa capital A, this is given, F prime C, beta 1, saka B. Tapos dito sa capital B, given din yung mga ipapasok natin dyan, AS, A prime S, F prime C, saka yung Fy. Ganon din sa capital C, you have A prime S, saka D prime. And then, ipapasok mo yan sa quadratic equation para ma-solve mo si small c, which is 214.28. And then, from there, since bago na yung small c mo, mako-compute mo ngayon yung bagong FSC, which is 398.39 megapascal. And then, step 7B-3, determine the ultimate moment capacity. Ayan. So, dito, dalawa na ang ating i-consider. You have the tension steel, which is defined by D minus A over 2, tsaka yung compression steel, which is defined by the lever arm na D minus D prime. So, ito yung kanyang magiging result, which is equal to 591.12 kilonewton meter. Okay? So, take note, dinivide niya ng 1 million para maging kilonewton meter. So, you do this with your calculator or your Excel. In a design problem, the material properties FC and Fy are specified by the designer. The design factored moment is determined from the analysis of the structure subjected to factored load specified by the NSCP. Furthermore, a beam will only be designed as DRB when subject to beam size constraints. Thus, in this situation, the beam size B and D or H is dictated. The beam cross-sectional size is then checked if this can resist the moment from factored loads as a singly reinforced, which is the first choice, only if the dictated size is inadequate to be designed as singly, that the section will be designed as doubly. To determine if the given beam section can be designed as singly, the maximum permissible amount of tension steel Rho max is determined to get the Rmax using equation 6. Okay, so ito yung ating Rmax is equal to rho max Fy times this quantity 1 minus rho max Fy all over 1.7 F prime C. From equation 7, the moment capacity corresponding to maximum steel limit for SRB is shown below. So Mmax is equal to Rmax times VBD squared. This value of Mmax is compared with the design factor moment, Mu. If Mmax is greater than Mu, then the section dimensions B and D are enough to design the beam as singly reinforced, and the design procedure for singly is followed to determine the required reinforcements AS. So, ito yung pang SRB na moment capacity, ano? Otherwise, when Mu is greater than Mmax, okay, kapag mas malaki yung load dito sa SRB na moment capacity, then that's the time na i-design mo yung beam as DRB. Diyan yung i-consider mo ngayon yung compression steel. In order to cope with the excess moment, Mu all over V minus Mmax. To do this, so ito na ngayon yung magiging M2 natin, ano? To do this, the nominal moment capacities will be divided into 2 as illustrated below. Okay? So, divided into 2 in the sense na meron kang M1 tsaka M2. So, yung M1, ito yung SRB. Okay? Take note na si SRB, ang compression niya is due to compression concrete only. Tapos, dinagdagan natin siya ng M2. Ito na yung compression due to your A'S. Okay? So, remember, bawat compression meron siyang katumbas na tension. So, si compression concrete magiging T1, si compression steel magiging TS2. In figure 3.9 above, the couple M1 in the section shown at the left represents the nominal moment capacity corresponding to maximum steel and the steel ratio rho max. Thus, AS1 is equal to rho max BD and TS1 is equal to AS1 FY. Equilibrium required that T1 is equal to CC, which is equal to 0.85 F prime C. This gives small a is equal to T1 all over 0.85 F prime C, and the nominal moment capacity Mmax is equal to M1, which is equal to TS1 times D minus A over 2. The section at the right, eto na, shows the required nominal moment capacity M2, which accounts for the remaining required nominal capacity to resist the total required nominal capacity Mu all over V. So, M2 is equal to Mu all over V minus Mmax. Okay, ano yung M2? Yan yung excess moment. So, yung Mu all over V, ito yung load, tapos Mmax, ito yung capacity moment ng SRB. Okay? With the known lever arm of D minus D prime, the amount of additional tension steel is determined. So, TS2 is equal to M2 all over D minus D prime. And from figure 3.9, AS2 is equal to TS2 all over Fy. Equilibrium requires that CS, ito yung compression steel, is equal to TS2. The force is in the compression bar is expressed as CS is equal to A prime S times FF press C, where FSC is the stress in the compression bar. The stress FSC is equal to Fy if these bars reach the yield point. Otherwise, the stress will be within the elastic range and determined using Hooke's law. Using similar triangles of the strain diagram, the expression for stress is with ES, elasticity of steel, equal to 200,000 megapascal. So FSC is equal to 600 times C minus D prime all over C. This should be lesser than or equal to Fy, where C is equal to A all over beta 1. When the stress FSC is established, the compression reinforcements A prime S can be determined easily. So AS2 Fy, this is equal to A prime S times the quantity FSC minus 0.85 F prime C. And your A prime S, this corresponds to your AS2 Fy all over FSC minus 0.85 F prime C. Okay? And the amount of compression reinforcements is determined last. This will depend on the stress of the compression rebars, which in turn is dependent on the location of these bars. If the compression rebars are near the beam surface, or small d prime, these bars will likely yield. If they yield, the stress will be FSC is equal to Fy. Otherwise, the stress is determined using Hooke's law. So, malapit na tayo sa pinaka-procedure. The procedure for designing DRB can now be summarized. The given data are the section properties. Ito na siya. B, D, and D prime, material properties, and the design moment. The design objective is to determine the reinforcement amounts, AS and A prime S. So, for step 1, ito na yung mga importante. Okay? So, solve for beta 1 and rho max. Then, step 2, solve for R max, which is equal to rho max Fy times this quantity, and M max is equal to R max times VBD squared. Remember na ito yung mga capacities due to singly reinforced beam. And then, step 3, compare MU and M max. Dito, pag mas malaki si MU kaysa sa M max, then, design mo siya as irregular. Okay? Kapag si MU, mas maliit kaysa sa M max, ibig sabihin, mas malaki yung SRB. No? So, i-design mo siya as SRB lang, or AS lang ang kailangan mo. So, ito yung importante. Case B, kailangan mas malaki yung MU kaysa sa M max. That's the time na i-design mo siya as irregular and proceed with following steps. Irregular means DRB. Okay? Step 4, determine AS1, which is equal to rho max times BD. Step 5, determine the required nominal moment M2, okay, which is based on your excess moment MU all over phi minus M1, where M1 is equal to your M max. Okay, take note na si M max is equal to R max times phi BD squared. And then step 6, determine the required amount of AS or tension reinforcement. Your AS is equal to, remember AS is equal to AS1 plus AS2. But what is AS1? Ito siya, okay? Tapos yung AS2 naman, ito yon. It is dependent on M2, which is this, all over Fy times the quantity D minus D prime. After that, we go to step 7, determine the stress of compression bars. You have small a is equal to AS1 Fy all over 0.85, and then you divide that by beta 1, masosolve mo si small c, and you can find the stress in the compression steel, which is equal to C minus D prime all over C times 600. But this is not to exceed Fy. And finally, step 8, determine your A prime S. Ito na ngayon yung compression steel, which is equal to AS2 Fy all over the quantity FSC minus 0.85 F prime C. The procedure to design a DRB is illustrated in the solution of the problem below.